Alright, in this video we want to find a basis for the orthogonal complement of this vector. Now I go a little bit more in depth in the next video, not that much, but for now we're just going to work right through it. The process is pretty simple. All you need to do is take your vector or your matrix and you need to transpose it and get the null basis of the transposed matrix. It's pretty straightforward. All we need to do is take all of the columns and turn them into rows. So we have 1, 2, 1. Don't forget your negative signs here, and then we're going to go ahead and rewrite this like that. Now we've already got this in pretty much the most, simplified version that we can have, so we don't need to do any row reduction or anything like that. But we have a pivot here, and then these two variables, x2 and x3, they're going to be free variables. So what we have here is that x1 minus 2x2 minus x3 is going to be equal to 0. And if we want to get x1 by itself, we would have x1 is equal to 2x2 plus x3. And then all we need to do is rewrite that in a vector form. Normally we would have x1, x2, x3, but instead we're going to replace x1 with this value here. So we have 2x2 plus x3, then we have x2 and x3. And now we just need to pull out each individual variable that we have here. So we'll have x2. You can see in the first row we have a 2. In the second row, we have 1 x2, and then in the third row, there's no occurrence of x2, so that'll be a 0. And then that's going to be plus x3. And then in the first row, we have 1 x3. Second row, we have 0 x3. And then the third row, we have 1. And we're all done. And it's a rule overall that when we have our vector v, we can see that here it is R3, because we have 3 different rows here. However, there's only one vector given, which means that it's one dimension, which means that the dimensions of our basis for our orthogonal complement, that's going to be equal to 2, because the dimensions of v plus the dimension of the orthogonal complement will always be equal to n, where n is Rn. In this case, n is 3, but if n were 7 and we had, 3 dimensions, then we can expect our complement to have 4. And that's about it for this video. I just wanted to cover the process, and we'll talk about it a little more in the next video and do another example. But these are our answers, and we can check to make sure that they're correct by doing a dot product between each one of these vectors and our vector v, because we want to ensure that the dot product is equal to 0. So what we have is 1, -2, -1, and we could do a dot product with 2, 1, 0. So we have 1 times 2, that's going to be 2, plus -2 times 1, that's going to be -2, and then -1 times 0, that's going to be 0. So we have 2 plus -2, which is going to be 0. That's what we wanted. And we could do the same thing with our other vector here, which is 101, 1, 0, 1. We see that we have 1 times 1, that's going to be 1. -2 times 0, that's going to be 0, so plus 0. -1 times 1 is going to be -1, so plus -1. 1 plus -1, 0. So there we have it. That's our answer.